Good morning, or depending on where you're joining us from, good afternoon. Thanks for attending this session. My name is Philip. I'm responsible for strategy and business development at the Bartis Group, and I'm joined by my colleague Daniel, our lead data scientist. Today we're going to be talking about creating a forecast for two different financial service industry use cases, and we'll be showing that in the demo later on in this webinar. Again, thank you for joining. Before we get into that, I just wanted to share some of this recent research from Gartner. Provided a very interesting framework called these 5 ways artificial intelligence and machine learning can deliver business impact. And we thought this to be a very useful framework that you could use. They've basically defined these 5 ways as innovation, exploration, prototyping, refinement, and firefighting. And then along those dimensions, they also provide how your data scientists might work, what those main objectives are, the plan, and how they might use data. Since we find this very useful, we thought we'd share this, and we encourage you to look this research up. It may help kickstart some of your own machine learning activities. Now, the application of machine learning in financial services is an accepted, well-established fact by now. New use cases pop up every day, and they're no longer confined to core banking functions. Now we also start to see applications in other areas of the business as well. Take, for example, human resources, FP&A, financial planning and reporting, IT, marketing, call center operations are a good example, as well as property management, and the list goes on. Of these, there are a few that can be described as time series forecasting problems. These offer tremendous business value, but have been notoriously challenging to implement. So before we get into why they're notoriously challenging to implement, let's talk a little bit about what is a forecast. We have a timeline with a past and a future. We sit at the present point in time, and we want to know what the value of our target variable will be at some time in the future. Predicting those future values depends a lot on the actual historical values that we've collected from past transactions. But it also depends on many other factors that might influence our target variable. These factors are called features by data scientists, and taking these into account, in addition to taking into account the actual fluctuations of our target variable, allow us to create a multivariate forecast. So creating a multivariate forecast, you actually have several options available to you. I'm going to highlight 3. You could try building what we call handcrafted models using R or Python, and using libraries like XGBoost and TensorFlow. And as the name suggests, all the work here is coded manually, and you need to be an expert to do this well. Notice that the model building process is recursive, and it takes several iterations before it can be deployed and become useful. You could also use one of the popular AutoML options on the market right now. DataRobot, RapidMiner, H2O, Dataiku are good examples. And these solutions do a great job automating the engineering steps. Notice this brute force method is also iterative and is designed to find the best algorithm. There's also a very key step, which is the feature engineering step, some of which is automated, but most is still very manual. And finally, we have Instant ML. This is unique to TangentWorks, which we're introducing today. Instant ML is a new category of model generating options on the market today. And TangentWorks, or Tangent Information Modeler, TIM for short, takes a completely different approach. And instead of trying to find the right algorithm, it determines what factors or features in the data are important. This is a game changer because by finding those features, TIM can produce a more accurate time series forecast in seconds. It's very easy to use and integrates well with other data tools. You can use it right inside of Excel, your favorite analytics platform, or perhaps think about scaling it up to big data platforms like Hadoop as well. An interesting side effect is that to build a forecast, TIM finds the most predictive features in your data. Sometimes, depending on your use case, this could actually even be more important than the actual forecast. If the features change as you're building these forecasts, it tells you that something in your business has changed. This is the essence of anomaly detection, a feature built right into TIM out of stand and comes right out of the box. Okay, so we alluded to some difficulty in creating time series forecasting. Time series forecasting retains something of an outsider status compared to more recent and popular machine learning topics such as regression, classification, or natural language processing. And although time series forecasting can be thought of as a supervised learning problem, time series forecasting problems have several unique quirks and idiosyncrasies that set them apart from typical approaches to supervised learning problems. This is going to require your data scientists to rethink their approaches to building and evaluating models. So let's look at what some of these potential idiosyncrasies might be. The first is changing data patterns. Phenomena represented by time series data are dynamic. Consequently, a working model is not guaranteed to stay up to date. Numerous examples in different industries illustrate this reality. Changing portfolio of assets, for example, in the financial services, will require rebuilding the model from scratch on a frequent basis. Previously valuable models suddenly become useless in these new situations. Rebuilding models, clearly, especially the traditional way, is clearly not an optimal solution, as it can take much time and effort. And then these new situations often require the data scientist to identify new significant features rather than being able to just tweak the modeling technique or using slightly adjusted hyperparameters. The second issue is data availability. And the availability of data can vary from time to time, and then certain data that was actually used during the building of the model might not be available when a forecast needs to be made. As a result of this unavailable data, the model cannot be used for forecasting. Finally, we have situations that require a forecast to be produced for multiple points of time in the future. This multi-point forecast for the prediction horizon, as opposed to a single point forecast in the future, which is called a single point forecast. Situations where only a single point forecast are required are actually quite rare, and multi-point forecasts are far more common. Multi-point forecasts have traditionally been addressed by multi-output models or recurrent strategies. Both of these approaches have their problems. If you go the multi-output forecast model route, models tend to exhibit a higher level of complexity compared to a single output model, which stands to reason, and often they can even result in a contradictory optimization problem that has to be dealt with. On the other hand, when using a recurrent strategy, the data scientist needs to be aware that a recurrent strategy is often prone to rapid divergence, which often renders them impractical for widespread adoption. So we introduced Tangent Works, or TIM, Tangent Information Modeler, and let's see how this solves some of these problems. TIM solves the problem of changing data patterns by allowing models to be either rebuilt or recalibrated continuously. Recalibration only adjusts the model parameters and leaves the model structure or features intact. And model rebuilding starts by identifying new features and then builds a completely new model. Through the identification of new features, the process of model rebuilding makes your forecast resilient to future change. And you can do this as often as you need to if the data changing patterns are very different. When data becomes unavailable, TIM has a data availability schema which is attached to each model building effort. So this allows TIM to take into account expected data availability conditions. If you know what those are, then this is the best approach. But when there's an unexpected change in data, TIM's instant ML capabilities can rebuild the model instantly from scratch using the constraints of this new situation. So we've got you covered there. And then finally, for multi-point forecast, TIM actually creates a set of single point models. And in this way, every forecast point has its own individual model that considers the corresponding data availability constraints. The collection of these sets of models is referred to as a model zoo. So a few words about TIM. It was named one of the top 10 most innovative ML companies last year. It's a fast, automatic, scalable, and easy to deploy forecasting and anomaly detection solution. It works by finding the right features, not by finding the right algorithm, which is a different approach to other products on the market right now. It can be deployed in the cloud, on-prem, as a web service, or on the edge. It's already integrated with a host of data products from multiple vendors, allowing you to make use of it wherever a time series forecast or anomaly detection is required. And it's priced on a consumption of forecast model, not how you consume it. At the end of this webinar, we'll be sending out an email, and there will also be a link on the last slide allowing you to access a free trial if you'd like to try it for yourself. Now, let's get on to the demo. Daniel, I hope you're ready. What we're going to be showing you is the first use case, which is an unemployment insurance claims forecasting use case. Daniel's going to take you into TIM Studio, which is the TIM web platform. He's going to create a forecast on the fly and do it dynamically by dynamically adding features. So this is going to happen instantly while you're watching the screen, something that in other products would normally be quite a long process. And then we're also going to look at a little bit under the covers, look at the explainable AI, understand what factors drove the creation of that particular forecast so that you can get some insight into the fact that TangentWorks or TIM is not a black box. The second use case, we're going to look at some data from Kiva, and we're going to create a forecast in Excel to again show you that the modeling engine is completely separate to how you consume the forecast. You could consume it easily in Excel. We'll also create one in Click, and then we're going to go on from there and really show you what the anomaly detection feature looks like and find some business impacting changes in these load and funding patterns. So I hope you're ready. Daniel, over to you. Thank you very much.
Okay, so we'll start with the unemployment insurance claims demo. So for this demo, we're using data from here on employment insurance claims within New York State. It's an interesting data set. It goes back to 2002. However, there's not really information in there which could be used to help make predictions for what insurance claims would be going forward in the future. So therefore, we layered in some other data, such as this new US National Home Price Index. So once we aggregated that data together and put it in the spreadsheet, it looks like this. So this is a classic time series data set, which you can tell from the fact we have this timestamp going down in this column, kind of increasing by 1 day at a time. Now, then we have the beneficiaries column. This is the number of claimants making unemployment claims per month within New York State. And in machine learning terms, this is what we call the target variable, because this is what we're trying to predict. This is what we're trying to forecast out in the future. We're trying to predict the number of claimants in the future. Now, a sort of simple forecast model might just use the historical number of beneficiaries as a way to predict the future. Like what happened last week might be the same again next week. So, that can be okay, but for a more sophisticated approach, it's much better to try to layer in other data if possible. But if you want to do that, then you also need a more sophisticated algorithm which can take care of multiple input variables. So we've added in these additional variables here, like this is the profits to earnings ratio, the consumer price index, and the US National Home Price Index. So we've added in these other variables, and TangentWorks allows us to make our models and leverage the information contained within these external variables rather than just using the historical number of beneficiaries to predict the future. So the first way I'm going to show TangentWorks and TIM is to show the Excel add-in. So I just click on this column, I select the data range that I want to use, then I select the target variable, which is the second column beneficiaries, so that's fine. And then I want to select the predictors I want to use. We're going to skip these two columns, so I'll just keep these economic indicators. And then I just have to forecast out have to decide what the forecast horizon should be. So this is daily data, so let's say we're just going to forecast out for the next week. So I hit the forecast button, and the Excel add-in is going to send the data. You can see extremely quickly we got our prediction back from the TangentWorks TIM API. So it just going to add in the forecast at the end. So not super exciting in terms of how it looks. It's just some numbers added to the end of the spreadsheet. So I think it will look more interesting when we look in the TIM Studio web platform. But one thing you may have noticed is that it was extremely quick. And because this is sort of normal for it to be this quick if you're doing a relatively simple forecast using only the target variable, the number of beneficiaries, as the input. But we're actually building a sophisticated machine learning model using information from all of these different variables, which is a much more sophisticated problem. So it's impressive that TangentWorks can do this in such quick time. So now let's switch to the TIM Studio web platform. So there are a number of different ways of using TIM. You can install TIM on-prem, or you can use the Excel add-in as I showed. You can also integrate it with a wide range of BI and ETL tools. But you also have the option of using the TIM Studio web platform. So let's take a look at that. So for now, we're looking at the unemployment insurance data. So we go to that workspace, and we can see the data set, which I've already loaded in. You can load in data as CSV or through a relational database. You can also load in data through the API. In fact, everything you see in the TIM Studio platform, you can automate via API. So here we see the number of beneficiaries over time. So this is just showing our sort of time series. You can see these sort of patterns. These are clearly like weekly periodic patterns. And then we see other patterns like this big spike here. We can layer in the other data, such as the economic KPIs. This is all normalized, so they appear on the same scale. If we turn that off, then these are on a much smaller scale than the number of beneficiaries, so normalizing helps us see that. We can also zoom in easily and zoom out. But okay, so that's just the raw input data. So now let's go ahead and make a forecast. Now the simplest way to make a forecast in TIM Studio is to go to the forecasting tab and make what's called an instant ML forecast. So that's where we select our dataset and then click on the lightning bolt icon to create an instant forecast. So all we have to do here is select, again, the prediction horizon. So again, let's forecast out 7 days into the future. So that gets added to the queue. But yeah, this is a sort of one-button approach to forecasting where we didn't really have to set any parameters except for just deciding what the forecast horizon is. So the black line here shows the most recent actual data. Then when I click on this, it shows us the forecast, which was just built. So the orange line is the forecasted data in the future. Now we're getting a warning message here that's using a weak model because some data is not available for some future timestamps. So that's not a huge problem for this particular forecast. Okay, so now let's look at the model in a bit more detail. So let's take a look at a model that's already been built. And this will give us a better idea of what TangentWorks is actually doing under the hood. So again, we see the forecast and we see the forecast against the actuals for the training data. But what I want to show you is this. This is the model tree map. So this shows which of the it shows the relative contributions of each of the input variables of each of the features. Now, an important thing in time series forecasting is that you don't just take the raw variables. The raw variables would just be, say, these three columns, the economic indicators and the number of beneficiaries. For time series forecasting, you generally have to do some transforms first to make those variables useful for forecasting. So for example, you might take moving averages, you might take lags. So for example, t-2, that means that's a 2-day lag of the number of beneficiaries, whereas this is a different type of transform applied to the profits over earnings. And then we have some other variables, again, based on P over E, a lag in this case, and the number of beneficiaries. So depending on the data set, like this tree map can get very complicated. There can be a lot of different features there. So this is kind of one of the big things that TangentWorks is bringing to the table, because you have to do these transforms, but you don't necessarily know what they are ahead of time. So there are a couple ways to approach that. You can do that through intuition, like through business intuition. Maybe you know that a certain sort of moving average window or a certain type of lag would make sense for a particular data set, which is fine, but that doesn't scale well if you want to do this for a lot of different data sets, or maybe if you may not have so much machine learning background, you may not find it so easy to figure out which the appropriate transforms are. So the big advantage of TangentWorks here is that it does this automatically, and it also does it very fast, because another way to figure out the appropriate feature transforms is to use brute force, so to try out lots of different combinations. Because you can see here, in this case, it's using an interaction term between two features, this lag of the beneficiaries and this other transform applied to P and E. So if you take all of the possible combinations and all of the possible transformations of each of the raw features, there's like a huge space of potential feature transforms which you could make. So finding the optimal ones through brute force is very, very time intensive and compute intensive. Whereas TangentWorks takes a different approach. It basically has a mathematical algorithm which finds the optimal feature transforms for this data set very quickly. So another thing we can look at is the experiments tab, which basically allows us to do backtesting to help us validate our model. So the way this works is we're going to take, or by default, it takes the first 2/3 of the data, and it will build a model on the first 2/3 of the data. Then once it's done that, we'll validate the model with the final third of the data. So, I clicked that build model button, and it built the model in a couple seconds there, and it's built an entirely fresh model during that time. We're not using a pre-built model, it's built an entirely new one. And now you can see, now we've finished validating the model. We can see the validation data set is in gold against the actuals in blue. Right, so this portion of the data, the final third of the data, we have the actuals for it, but we're calculating the forecast. The important thing is that the model has not seen the data that we're forecasting here. So you can see it's impressive, like how it matches the actuals pretty effectively. It's captured a lot of the complexity of the patterns, like the weekly cycles that we see, and also this recent trend of sort of decreasing claims over time. So now let's skip to the second demo, which is using some data from Kiva, which is a company that provides loans for social good. So they provide loans to economically underprivileged communities around the world, allowing people to access finance sort of wherever they are in the world. So the data comes from here and loaded into Excel. It looks like this. So again, this is time series data. Again, we have a timestamp with a regular frequency timestamp, again going up daily. And then we have this is the amount, the funded amount of loans on that particular day. And this is our target variable in this case. This is what we're trying to predict. So we're trying to forecast out the amount of loans funded on each day going forward. We also have the amount of loans applied for, and the median loan term in months, and the median lender count, because Kiva uses a crowdsourced loans model. So there are multiple lenders for each particular loan. And then these are the three different payment types. So there are bullet, irregular, and monthly loans. These are just the counts of each payment type for each given day. So again, these are the variables which we're trying to use to help us forecast the funded amount. So we've already seen the Excel add-in, so I won't show that again. So I'm going to skip straight to Tim Studio and just show the results from there briefly. So we can look at the model definition page, and let's take a look at the tree map first to see which features are going into the model. So you can see this one is a bit more complex. The more features you have, the more input variables you have, the more complex these tree maps will be. These ones are relatively simple as far as these types of data sets go, but this is obviously just for demo purposes. But still, this one does have a bit of complexity. So we have the loan amount. The historical loan amount is obviously being a major predictor. And there are some other interaction terms here. We have the payment type being irregular, the count of those, some transform applied to that, and so on and so forth. And the lone term in months is important there as well. So this tree map kind of goes beyond just getting predictions out of the tool and getting towards the concept of explainable AI, which is a big thing in both in the sort of academic field of data science and industry, because in many cases what you're looking for your business use case is not just to get predictions out of a black box machine learning model. You also want to know why those predictions have been made. So this sort of thing can help you get to that point. Okay, so now let's switch to take a look at another feature of TangentWorks, which we can run on this data set, which is anomaly detection. So this is basically just kind of flipping the time series forecasting idea around. And basically what we do is build a forecast model, exactly the same algorithm as we saw being used before. But in this case, we're comparing the results to the actuals and setting a threshold beyond which any any data point is considered an anomaly. So let's take a look at this anomaly detection, these results, which are already built. Again, the modeling process is extremely fast and takes the same amount of time as building any other forecast model in TangentWorks. It's a couple seconds. So the blue line shows the funded amount over time, and the red blobs show the anomalies that have been detected. So notice that the red blobs are not just showing, if I turn off normalize, they should fit on the data better. Notice that they're not just where there are high values and low values. In some cases they are, like this is a bit of a spike, there are a few spikes here, but notice like this spike, for example, did not get flagged as an anomaly. So TangentWorks is not simply looking for high and low values. What it's doing is building a forecast model using the regular sort of sophisticated machine learning driven algorithm, and then it's comparing those predictions to the actuals. And that's kind of what we see in the second chart here. Here we see a line chart showing the difference between the actuals and predictions. And you basically set a threshold, so anything above this threshold where the difference between the prediction and actual is more than that amount will be flagged as an anomaly. So you can see like these two guys here, we have red flags for those, and same for these things. But notice this big spike here, although it's a big spike, it's not actually that different. It's probably this spike here, so it's a bit different maybe, but not that different. It's still within normal bounds. And then, so the threshold is a parameter that you have to set manually, and you can basically adjust the threshold. If you had it higher, then you'd get less anomalies coming through, but they'd definitely be, worth looking at. Whereas if you put the threshold lower, then you'd have more anomalies coming through, but you might have a bit more noise coming through as well. You might have some data points being flagged as anomalous when really they're actually okay. So you can adjust that threshold based on sort of that payoff between noise and signal, basically. So now let's switch to take a look at the quick TangentWorks integration. So this is the integration that we have built, and again we see the raw data as a time series here. So this is just the funded amount over each day, and then we also have the raw data showing here. So we have our timestamp column, the funded amount, and the other predictive variables which are going into the model. And then here we see the forecast. This is just a 7-day forecast against the actuals in blue, and then we again see the tree map, which shows the feature transforms which have been made automatically. This is a different tree map which shows, instead of showing the transformed variables, it shows the influence of the raw variables themselves, even though the raw variables are not sort of being directly used by the model, but it still gives you a good idea of which of the raw variables is actually in use. Like this is the funded amount, and this one shows the lender count. So there's actually like a little bit more information you can get through the API in that sense, compared to just the Tim Studio platform. The main sort of type of interactivity we have here, or an example of that, we can change the forecast length. Let's say we want to forecast out the next 30 days instead of the next 7 days. Let's try that and see how that looks. So again, the result comes back very quickly, and we can see our forecast compared to the actuals. And we have a different model, slightly more complex set of feature transforms in this case. So the way this is implemented in Qlik is using a server-side extension, which may be familiar to those of you who use QlikSense. It's basically a way to extend the BI tool Qlik with custom functionality, which you can write in Python or R or Java or a number of other languages. In this case, it's in Python. So basically, the Python code just takes in the data from Qlik as we select it. It takes in the raw data that's shown here and the chosen forecast length. It then sends that off to the TIM web API. Tim makes a prediction, sends that back to the Python code, and then the Python code provides that back into QlikSense, where the results are then displayed on the screen. Similar sort of process for other BI tools. We have similar integrations for Power BI and a number of other tools. So I think that's everything I wanted to show for the demos.